Dr. Stefano Pirandola. He is a Marie Curie Fellow of the European Community, affiliated with both MIT and University of York. He got his laurea degree in physics from University of Rome La Sapienza, and then PhD from University of Camerino in Italy. And he's going to talk about quantum state discrimination with continuous variables.
Okay, thanks a lot. We'd like to thank Vishal for having invited me today. So yeah, this is a work that I've done mainly at MIT very recently, together with the other people there, Seth Lott, Jeff Shapiro, and other people like Vittorio Giovannetti, Lorenzo Marcone, and so on. So this is quite a general topic. So in fact, we start with just a general description of the problem of quantum state discrimination. And here I will give just the basic tools that are connected with this problem. But then we will consider in some sense an extension of this problem, which is the quantum chain discrimination, which is more interesting for us because this problem here has several interesting applications. In the case of bosonic systems, one of these is an application to the detection of a target that we call quantum illumination, and another one is another application is for improving the readout of digital memories using these tools. So basically, these two parts. I try to be fast because this is a very long actually talk. It's a fresh-made talk. And I will try to go here very within the time. Okay. So okay, this is just okay. The first problem is the quantum state discrimination. So suppose that we have two possible states, rho 0 and rho 1. And these two states are given with the same probability, but we don't know if we are given this one or this one. So there is 50% of probability that we have hypothesis H0 or hypothesis H1. So we have this binary test at the beginning. And well, our aim basically is to distinguish between these two possibilities. And in order to do this, we consider here quantum measurement to be applied to this unknown state. And the outcomes of this measurement are in general designed to discriminate the two possibilities. So this is just a dichotomic detector whose outcomes discriminates between the first hypothesis and the second hypothesis. And the problem here, this is a quite general problem. The question here is, what is the minimum error probability affecting the discrimination of H0 and H1? Because of course, in general, we have here two states which are non-orthogonal. As a consequence, since these are non-orthogonal, we have some error probability here in this discrimination, meaning that the detector can click this outcome here when actually the real hypothesis is H1, or the detector can click this outcome here while the real hypothesis is H0. So this gives an error probability. And we want to know what is the minimum error probability for this problem. Okay, this problem can be set in a different way, a current way. So basically, we have a logical bit, U, that can take a value 0, 1, encode it in a quantum state. Then we want to decode the bit using a quantum measurement. And then we ask, what is the minimum error probability in the bit decoding? Basically the same thing, stated in different words. Okay, actually this problem has a general solution. This is known. Elstrom solved this problem. The minimum error probability here has a very nice expression. It's basically a function of this quantity here, which is called the trace distance. And it's basically given by the trace of the modulus of the difference between the two density operators. So it's a very beautiful and simple formula to see what is the minimum error probability in this, for this task. And not only we know what is this error probability, but we also know what is the optimal detector. So this detector here basically can be described by a POVM having only two measurement operators. One POVM, one operator here is just the projection on the positive part of this quantity here, which is called the Elmstrom matrix. And the other measurement operator is just the closure. It just gives the closure to the identity. But it's just, okay, mathematical details. Now, the thing is this, that, okay, so we have this problem. We want to discriminate these two states. And we want to, we want to understand, we want to compute this error probability. So in order to compute this error probability, we have to compute the trace distance between the two states. Now, in general, this is not a very easy quantity to compute because we have basically a difference between density operators. While it is much better to have a quantity which is a function of powers of density operators. This is much easier to compute this kind of. So what we do usually is to look at upper and lower bounds, which are based on powers of density operators, and then we use these upper and lower bounds to estimate this quantity and the error probability, basically. So one of these is the fidelity. So the fidelity between the two states. And if you see here, you have basically a product of powers of density operators. And the other one is called the quantum chain of bound, which is a bit more difficult. More difficult to compute, but it's still feasible. And here we have, you can see we have a product of powers of density operators. The most difficult part here is this minimization, but you can actually do that. And so using these two tools here, the quantum chain of bound and the fidelity, you can write this upper and lower bound for the error probability. And this is actually a quite recent result, this upper bound here. But there's another thing here, is that, okay, if you have an M copy discrimination, so for instance, you have an input state here, which is given by a tensor product of M different copies, each one encoding the same logical bit. And we want to discriminate, okay, this tensor product with a coherent measurement here. What we have is actually that we can use in this setup a property of the fidelity, the quantum chain of bound, which is the multiplicative under tensor product of density operators. So basically, they are, if you have here a tensor product, you can put this m to the power here. So this is quite a remarkable property. And using this property here, you can write this upper and lower bound. So this is basically the error probability for the M copy discrimination. So this problem here, where there are M different copies of the states. And these are the two upper and lower bounds, where here the quantum channel bound is actually computed over a single copy. So not on all the states, but just on a single copy here. And also the fidelity. So this is very, very useful from a mathematical point of view, But more interesting is that when you take the number of copy going to infinite, you have that the quantum channel bound actually gives the error probability. So it's a very good estimate of the minimum error probability. So usually if you have a problem where you have many copies here, encoding the logical bit, the smartest thing to do is compute the quantum channel bound, because asymptotically it gives the error probability. Now, suppose that, so now we have considered this problem of discriminating between two states, basically quite a general problem. These two states can be a tensor product. And we have seen that the quantum channel bound is a very important tool, because it gives a very good estimate of the error probability, and it's quite easy to compute. Now let's see what happens when we have not just two general quantum states, but two Gaussian states. So what are two Gaussian states of a bosonic system? So what is before a bosonic system? So a bosonic system is a particular quantum system that can be associated with a phase space. So it is basically a phase. So this is a space, like vector space, having two axes. So this axis basically describes the position, basically position operator of the system, and this is the momentum operator of the system. And so you can associate to the Hilbert space this two-dimensional real vector space. Now, a state in the Hilbert space corresponds to a Wigner function here. So it's pretty similar to a probability distribution. And the state is called Gaussian when this Wigner function is Gaussian. So it's quite a simple definition. And in this case, when you have a Gaussian state, you have you know that, if you have a Gaussian, the Gaussian can be completely characterized by the two first statistical moments, so just the mean and the variance. So here is the same. So this state can be characterized by the displacement. So how the state is far from the origin, the zero, which is the vacuum state, and the covariance matrix, which gives you basically the noise, the quantum noise of the state. So how much this function basically is spread in the phase space. So actually, so for a Gaussian state, you can when you have a Gaussian state, you can associate two quantity. The statistical moments, the covariance matrix, which is just a real matrix, and a displacement vector. And so when you have two Gaussian states like this, so you have two Wigner functions, you have statistical moments for one and the other statistical moments for the other one. And from these quantities, we can easily compute the quantum channel bound. In fact, one thing which is very useful in this trade is to compute the so-called symplectic decomposition of the covariance matrix. So this symplectic decomposition is a tool that associated to a matrix, a covariance matrix, a spectrum called the symplectic spectrum, and a matrix that performs the transformation. So this is quite, these are mathematical details, but what happens in the phase space? Basically, when we apply the symplectic decomposition in phase space, we have something like this, that the two asymmetric Wigner functions are transformed into symmetric Wigner function, having the same noise in Q and P, and so they are in a very good form. But this up to, we have this final representation up to using two matrices, two transformations. So using the displacement of the two states and basically their symplectic decomposition, we can compute the quantum channel bound for these two generic Gaussian states. And I mean, the formula is quite easy, but I mean, I prefer not to give too many details, mathematical details. But this is basically all the ingredients that you need to compute this quantity here. Okay, so this is basically the problem, two states. And when these two states are Gaussian, actually we have like a recipe to compute the quantum Shannon bound. And this quantum Shannon bound allows you to compute the minimum error probability when you want to discriminate between these two Gaussian states. Okay, now the next step, which is the quantum channel discrimination. So, what is a channel? So a quantum channel is a map, completely positive with trace-preserving map, that acts on the phase space of density operators. So you have an input density operator, you have a map, which gives you an output here, which is another density operator. Now, we have this problem. This problem is that, okay, you have here a channel, and you don't know what is the channel. This channel can have two possible forms, two possible expressions, E0 or E1, given with the same probability, but we don't know, I mean, a priori we don't know what is the, of course, this is just 50% this or 50% this. And we want to discriminate between this case and this case. So now, we don't have two states, but two channels. Okay, again, here we have that this channel can basically, basically encode a logical bit. Now, if we put here an input state, we fix an input state, since we have two possible channels here, at the output we have two possible states. But this is quite easy not to understand. And if you put here, of course, a detector, we have a detector. We can put here a detector where, I mean, the outcomes basically discriminated between the two possible output states. And this is, of course, a discrimination. For a fixed input state, this is, I mean, this gives you the discrimination between these two channels. And in this problem here, for discriminating between E0 and E1, or if you want the logical bit encoded in the channel, of course we have a price to pay, which is the error probability again. But now the problem is more, of course, is more complex, because we want to know what is the minimum error probability in the channel discrimination. And in order to know the minimum, we have to optimize not only on the detector, but also on the input. So we have a double maximization here. Input here, the state, and the optimal detector that we have to use at the output. Now, I will say, okay, if we fix the input, now we know that, so we fix the input for a two possible channel. We have two possible states, and we know what is the optimal detector, and also we know what is the error probability in that case. I mean, it's just the Elstrom bound that we have explained before. But of course, as I said before, we have to also to minimize now over the input state, rho, and the minimization of this quantity over all the input state gives you the minimum error probability for discriminating between the two channels. Now, okay, this is not an easy problem, and in particular, it's very difficult here to see, not just to compute this quantity, but also to understand what is the optimal input state. So on the one hand, we want to know what is the minimum probability, but it's more important to know what is the optimal state that I have to consider here, the input, in order to minimize the discrimination between the two channels. So this is actually, I mean, just to simplify the picture, because we have a more general description here. Because in general, we can consider, okay, we can consider many uses of the channel. So this is always the same channel here, encoding the same bit. So these are always the same, basically these are all replica of the same channel. encoding one bit, only one bit, U. But we can use the channel many times. This means that we can use an input that, which is a multipartite state, for instance, an entangled state, at the input of all these channels. So using M, for instance, M times the channels. And then we can consider here a coherent measurement of all the output that gives you basically, okay, the discrimination between the two possible values. But we can even have more. So a more general description, this one. So we have here the channel that we want to discriminate. We want to know. We have M uses of the channel. So we can imagine that we are using here M signals, which are probing, which are sent through the channels to probe the channel. But we also have another bunch of bosonic modes that we just use for helping this process. So these modes are directly sent to the detector. And the detector makes a coherent measurement over all these output here, but also over these idlers, and gives you the two possible values. So this is the most general situation that you can consider in order to discriminate between the two channels E0 and E1. Okay, so of course in this situation we want to know what is, the general problem is what is the optimal state here that gives you the minimal error probability in the discrimination between the two channels. So this is basically always the problem, but in a more general setup. Of course, this is not an easy problem. And we have a connected problem, which is easier and more interesting. It is just individuate. One very interesting problem, especially for the practical applications, is to individuate situations like channels where if we put here a truly quantum state, for instance, a state with entanglement between the signals and the idlers, then this state is able to outperform every classical state. So now we want to look to an easier problem, not just finding the optimal state here, but we want to understand what are the situations where the use of entanglement between the signals here and the idlers is sufficient to give you an advantage, is sufficient to outperform every classical state that you can put here. Of course, in this problem of channel discrimination. But what does it mean, a classical quantum state? So in general, the input state here, this input state can be decomposed using the P representation. So it can be decomposed in terms of coherent states, multi-mode coherent states. And this function is called P function. This can be very singular or not. It depends on the state. In particular, this state, when this state is called a classical state, when this function here is positive, a positive function. So this means that this P function is a probability distribution, and therefore this state can be represented like a classical mixture of coherent states. So this is the definition of the classical state in quantum optics. So it's something which is very close to a coherent state, but up to a classical probability distribution here. Otherwise, if this function here is not positive, then the state is quantum. And this situation here includes entangled states, Schrödinger-Cat states, so all the exotic states which are really interesting in quantum optics and quantum information. So we want to see these two cases. So for this case here, we have, so in the problem of channel discrimination, we can use, as an input, we can use a quantum state for instance, with entanglement, or a classical state. And if you use a quantum state, we have some error probability here, some quantum error probability. If you use a classical state, we have another classical error probability. And we are interested into explore the situations where we can actually put this inequality here. So this means that the use of a quantum state is able to outperform the use of any classical state. This is our goal. And this happens when we want to discriminate the Gaussian channels. So Gaussian channels is, in some sense, the equivalent of the Gaussian state. This just, to go fast on this without too many mathematical details. So a Gaussian state, we see that a Gaussian state basically is a state that can be described in phase space with a Gaussian Wigner function. And the Gaussian channel is just a map, is a CPT map that if you have at the input a Gaussian state, at the output you have a Gaussian state. So it's just, I mean, it's a channel that preserves the Gaussian character, I mean, the Gaussian features of the quantum state. Okay, I will skip this. Yeah, because these are just mathematical. Okay, so we have the problem again. So we have this. So this is the general, I mean, the channel discrimination problem for Gaussian channel. So we have this general problem where we have a channel here that can have two possible expressions, but now these expressions, these forms are Gaussian. So these are two possible Gaussian channels. And of course, we want to discriminate between these two. And we want to see where the use of a quantum state outperforms any classical state in this discrimination between these two Gaussian channels. So these are the steps that are usually considered. We fix the spectrum of the signal. This means that we fix you have to fix the number of signals that we are using to probe the channel here. Then you also fix the number of photons that you use for probing each channel. Then you can add, I mean, arbitrary number of idlers. And so you consider a state with these properties here, where these properties are fixed. And then you consider an output measurement, which is an optimal measurement. So this is the situation. And now you want to consider two cases. So in one case, this state is a classical state. So it is just a mixture of coherent states here. In the other case, this is a state which is truly quantum. So you cannot represent this state as a mixture of coherent states. And for instance, this can be an entangled state between this part and this part. And you have, as I said before, you have the two possible. So you have the error probability for, in this case, using the classical state for discriminating the two Gaussian, the Gaussian channel. And you have the quantum error probability here, the corresponding one. And we want to compare these two. Now, here we want to consider any classical state. In order to do this, we consider a lower bound of this error probability. Here, this is a lower bound that can be computed quite easily from this bound just depends on the spectrum. So it just depends on the number of the signals that we are using for probing the channel and the number of photons. And it's quite easy to compute because it depends on the fidelity here, where this fidelity is just computed over a single use of the channel. So it's a very, I mean, quite easy to compute. So in order to compute this quantity, you just have to consider a coherent state at the input of a single use of the channel, and you have to consider the output, the two possible output. This quantity here is the fidelity between these two outputs here. You put this quantity here, then you have to take the power of m here, and you find basically this bound, which is a lower bound for any classical state. So this is very, actually this is the most important part of the mathematical derivation. And this other part, we want to consider quantum state here. So we want to see if a quantum state outperforms any classical state. So here, for quantum state, we consider a EPR transmitter. So what is an EPR transmitter? Basically, we are considering as a state at the input here, a state which is given by a tensor product of EPR state. So an EPR state is a state that distributes entanglement, at least in this configuration, between one signal and one idler. Then one signal and one idler. So we have entanglement between these and these, these and these, and all the other, okay, in the middle. So we use this kind of input state. And for this kind of input state, we have an error probability that we can write, and we can upper bound this error probability with this quantity here, where this quantity here is just the quantum charm bound, because to compute this, you have just to consider the one copy of the EPR state sent to the channel, and the other is the idler. Then you have the output, and from the output you can derive the quantum charm bound, and then you can consider this quantity here. So what we want is this. So we want to find a situation where basically we have this inequality here. So this lower bound is actually bigger than this upper bound, because this situation here, which is easier to study, is a sufficient condition to have this condition here. The error probability for the quantum transmitter less than the error probability for any classical state. So the problem is that to find the situation when we have this, so what are the Gaussian channels and the signal, the typical signals where we can have this situation here. And actually this occurs when we want to discriminate, particularly we want to discriminate the Gaussian channels where the main effect is introducing losses and also thermal noise. So this is the typical channel discrimination where we have this situation here, but also when we consider a few photon signals. So the thing is that suppose that, okay, we have a Gaussian channel. We don't know what is the expression of the Gaussian channel. We can have two possible expressions. And we want to discriminate this, and we use very few photons at the input. So this is the conditions. And now we want to find which are the channels where the use of entanglement at the input is better, outperforms the use of any classical state at the input in this task. So this is basically the general problem. Okay, so the first application of this is quantum illumination. So this is so maybe this will make everything more clear. So suppose that you have here in a region of space you have a target, which is an object that can have two possible reflectivities. So you can imagine this like a mirror that can have or zero reflectivity or a very, 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 very small reflectivity. And we want to understand if this object is there or not, basically. So we want to understand if the reflectivity is zero or if the reflectivity is small. So if the reflectivity is zero, is like, okay, there's no object, is very small, but is different from zero, then means that, okay, there is an object there, even though this object is the reflectivity is very low. So we can design a situation, a detection like this. We can consider here a transmitter, which is a source of light described by some state, which is completely general now. This is just a completely general state for now. And these states describes M bosonic modes. So these are M bosonic M modes of the radiation directly shined to the target. But we have also other M bosonic modes which are sent directly to a receiver. So we have these signals here, these M signals shined over the target. Then we have the possible reflection of the target. And here at the output, we have a measurement. We can consider a measurement, which is in general, we can take this as an optimum measurement, which combines the reflected modes and the idlers here. And these two outputs here, 0 or 1, discriminate the presence or not of the object. So if U is 0, there is no object. If U is 1, we have the object, even if it is very small. We also have we also want to consider the situation where these photons here, so the signals are actually very weak. So these modes have very small photons, and the situation where here the receiver not only gets the reflected beams and the idlers, but also the thermal bath of the environment. So, and we also assume that this thermal bath is very high. So we have a situation where we want to discriminate the presence of a low reflectivity object using a few photons and in the regime of a bright thermal bath here. So if you look here, so here we have basically the situation that I described before, because these two reflectivities, R0 and R1, basically if you see the math of this scheme, gives you two Gaussian channels. So we have basically two Gaussian channels which corresponds to to these possible reflectivities. So this is just a practical implementation of the problem that I showed before. So we have the two cases now. So this state here can be a classical state. So basically without entanglement, if you want. So this is just, I mean, it's actually a weaker condition. So it's a classical state with just, I mean, something which has no entanglement, but can only have classical correlations between this and this. And this is a situation where the state is an EPR state. So here we have a quantum correlation between the signal and the idler. So it's much stronger correlation between these two sets of modes. And we want to compare the two, so we want to see what is the performance in the two cases. So if we are able to discriminate better in this case or in this case, to discriminate the presence or not of the object. And okay, this is just the numerical result. Basically, there is an analytical derivation, and finally we can plot this numerical result at the end. So this is actually just the regime that we are considering. So the object is the reflectivity is very low. The photons are very low, so we are just sending just 0.01 photon per mode over the target. This is the thermal noise, which is quite high, 20 photons. So this is the regime that we are considering. And this plot here is basically the error probability in the logarithmic scale for discriminating the presence or not of the object, so for sensing the object, as a function of the number of signals. M is the number of signals that you are shining over the object. And here is the performance of the quantum state, the EPR transmitter. And here is the performance of the classical transmitter. And actually, this is if you look at this, I mean, this is a logarithmic scale. So this actually, the improvement is very remarkable, because if you see, for instance, this point here, you have something like 10 to the minus 10 for the quantum transmitter. I mean, the error probability is very low, but we have just 2 order of magnitude difference with the classical transmitter. So the classical transmitter is only 10 to the minus 8. So basically you do 100 times better. Basically this means that you can discriminate a target 100 times better than before. This is basically the result. And yeah. Okay, so we have also the case for the coherent transmitter, but this is so if you consider here not just any classical state, but if you consider just coherent state, so if you compare the quantum state, the EPR transmitter with the coherent state transmitter, so now it's a particular classical transmitter. You see that the difference is even bigger, and in this case, just don't see this. This is just the asymptotic behavior. Just what is important here is to see this difference here. That means that if you are using entanglement, basically you are able to perform 4 times better in the error probability exponent with respect to using coherent states. And this is a pretty remarkable thing, actually. So I don't know how much time I have. Okay, 10 minutes, good. So I can do also the other application. So this is the other application. So consider a memory which can be built like this. So a memory where each cell here is a reflecting surface, is a B-splitter, basically. And each of these B-splitter here, you can encode a logical bit. So you have a bit that can have two logical values, 0 or 1. And you can imagine that you encode the 0 value in the reflectivity R0 of this B-splitter, and you encode the value 1 in the reflectivity R1 of this B-splitter. So basically, you have a logical bit encoded into the reflectivities of a B-splitter. So it's just a classical, so this is a classical memory. So this can be, for instance, total reflectivity 1, and this can be half or 0 or whatever. So this is quite general. So you can have an array of these cells here. So you can encode, for instance, here, okay, you have a bit 1 in this reflectivity, for instance, higher reflectivity, 1 higher reflectivity, 1 in the higher reflectivity R1, then you have a bit 0 encoding the lower reflectivity R0, and so on. So you can encode a string of bits in all these reflectivities of this array of B-splitters. So this is just a toy model for a memory. Okay, now you can consider, okay, a light that is able to resolve a single B-splitter. So this can be, for instance, a microscopic memory, where each of these guy here is a very, very tiny thing. So suppose that you have a light that is able to resolve these, resolve it, and then therefore address this cell. And you can imagine, again, a setup like this. So we have here a source, signals, M bosonic modes here, each one with n photons. Then you have the reflection. Then you can always consider the presence of additional modes here sent to the receiver. And then you have the receiver, and the detection of the receiver gives you the 2 possible values of the bit which are encoded here in this target cell. Okay? Now for now, this is just a general setup that you can design. Okay, in general, you have to consider noise. So noise means that you can have decoherence here. So this can be this general thermalization. So you have thermal noise within this system here. But you can also have stray photons scattered from the background, for instance. This is just if you are using during the day, if something like this, you can have this kind of noise here. So you have to consider decoherence also. And so if you look at this scenario, so you have something like this. So this is a row with this guy. Then we have here the idlers, here, which is this part here. And then we have this part here corresponds to this part here, where this U basically is encoded in a quantum channel. So this is just a practical implementation of the previous general scheme, the previous general problem about. So basically, what we are doing here, we are just doing a discrimination between two Gaussian channels. Okay. So we have two situations now. So this rho can be a classical state, so something which has only classical correlations between the signal and the idler system. And basically, okay, we can consider here for any classical transmitter, we can write this bound, as I showed before, for the error probability. So basically, this bound gives you an information of, gives you an estimate of the number of bits, the amount of information that you are able to retrieve from the target cell here using this classical transmitter. So we are able to, using this guy here, we are able to estimate the number of bits that you are able to retrieve from the cell, from the target cell, using the classical state. So using this classical state. But we can consider the case we have a quantum reading of the memory. So this is no longer a classical state. So we have no classical, so we have basically an EPR state here, meaning that we have entanglement between this guy here, the signal, and the idler. And in this case, we can use the previous formalism again. We can use, we have, of course, an error probability for the discrimination. And using this, the quantum channel bound, we can estimate the number of bits again that we can retrieve from the memory using this EPR transmitter. So what we want to see is this. We want to compare the two situations. So the situation where this guy is entangled, so is an EPR transmitter, is a quantum state, to the case where this is a classical state. And we want to see, we want to compute this quantity here. This quantity here is basically an estimation of the bit of the information that you are able to gain using the quantum transmitter instead of the classical transmitter. So basically, this G gives you the amount of information that you gain from this. So because for a quantum transmitter, you have, for instance, I don't know, 0.1 bit. For the quantum transmitter, you can have 0.2 bit, okay, decoded from this target here. So G is basically the difference. So it's 0.2 minus 0.1. So if this difference is positive, this means that the quantum transmitter, the use of entanglement is better, is outperforming. Now let's see what happens. So we consider, okay, a situation with actually low noise, but this is actually quite a moderate decoherence. Actually, it's quite a huge decoherence for the optical case. So we consider here the case where this transmitter is shining a few photons, so not so many photons, like 5 photons, a total of 5 photons, for instance, over the memory. I mean, I'm just putting in some numbers to see what is the performance. And then we want to find, okay, what are the memory where we have an improvement? So we want to understand what are so when in the presence of decoherence, in the presence of small photons here, what are the memory where the use of entanglement here gives you an advantage? This is the problem. And so this is just numerical plots, numerical results. So which derives from the previous formalism. So basically, these are the reflectivities of the memory. So these are R0, is one reflectivity. These are the other reflectivity. Okay, these are just, the value of the means that the 5 photons using only. This means that we are just sending one mode with 5 photons. Yeah, and we are comparing when these photons are entangled or not. And the black areas gives you the point where G is positive. So it means that for these reflectivities, the use of entangled photons gives you an advantage. And actually, okay, you have that these black areas becomes wider if you decrease the number of photons, but if you increase the number of signals. So basically, we are always sending 5 photons on total, but here we are sending just 1 signal with 5 photons. Here 10 signals with 0.5, 100 signal with 0.05 photons for each signal. So basically, but what is important here is to see that we have always this black region. These black regions always are basically describes. So you have basically this advantage using entanglement when you have this point here. This is a black point. So this means that if you use entanglement, you can increase the readout of the memory. Okay. So this is just, don't look at this, just look at this. This gives you the advantage that you can gain. So this is the G. When this G is equal to 1, means that for a classical reading, so if you use a classical correlations, you basically are not able to read anything. But if you use quantum correlations, you are able to read all the information from the memory. So the enhancement is very huge. Yeah, okay, so I'm almost finished. So what is the general consequence of this quantum reading is that, okay, you can read memories, digital memories which are unreadable by classical means. For instance, if they are too much damage, actually, you're not able to do that with classical light, but if you use quantum light, you can do much better. So you can read a memory which is damaged. Okay, you can increase the capacity of the memories because, okay, if you're able to read better a memory, then you need to use an error correction overhead which is big in the memory. So basically, you can reduce the error correction overhead in the file system of the memory. So you can increase the capacity for storing logical data. Another thing is that, okay, all this is true. All this enhancement is actually true when we are considering few photons, as I said. So the few photons regime. So few photons regime means that for a fixed power, if we fix the power P, few photons, so N is the number of photons here, means that you can make tau low. So tau basically is the duration of the pulse. So basically, means photon means that you can increase the number of you can decrease the duration of the pulses. So you can increase the transfer rate. But for fixed power, if you fix the power, less photon here. So if N is less, this means that nu here, the frequency can be higher. So this means that you can increase the frequency of the light. So if you increase the frequency of the light, it means that you can resolve small features on the memory, on the surface of. So if you suppose that you have this memory like a compact disk, so you can resolve smaller feature, and then you can use memory cells which are very, very tiny, and then this means that you can physically enhance, you can physically increase the capacity of the memory. So this is particularly important because when using the few photons regime is important, especially at the ultraviolet regime, because when you are using photons at this regime, at the ultraviolet regime, these photons are so energetic that they are able to destroy basically all the organic-based optical memories. And so it's very important to use few photons when you are increasing the frequency of the light. So basically what it means that using this kind of quantum reader enables you to decrease the wavelength of the light So decreasing the wavelength of the light means increasing the energy of the photons. But if you increase the energy of the photons, you can destroy the memory. You can melt your memory, because the memory usually is I mean, like the components are made by organic material. So the solution is just to, the solution of using quantum light is that, okay, I'm using energetic photons, but I use very, very, very few photons, because I can do that, because since I'm using quantum correlation, I'm able to use very, very, very few photons. So these few photons, even if they are so energetic, they don't destroy the memory. Okay, so yes, because this is a practical, because if you consider, for instance, the Blu-ray discs, now the Blu-ray discs work at 400 nanometers, which is the border for the ultraviolet range. If you go below this border here, you have something which is called the UV degradation of polymers. And this means that your CDs and DVDs basically are melted. So basically you have the information on the CD, but when you are going to read the information, you destroy the information, because the organic material is too photosensitive at this ultraviolet range. So if you want to have like a compact disc, for instance, which is whose density is very high, so a compact disc with a very high capacity, but at the same time a compact disc which is made by organic material, so you have to use few photons. Few photons means, for me, quantum reader, so using a quantum light. Yeah, so this is basically the, so this is like the very few last. So for instance, one can extend this as to realistic memory like optical disc. So if you see the readout from a compact disc, the readout from a compact disc is like this. So it's based on the reflection of a laser, like this pointer, from these different regions here. The pit, which is just a flat portion on the reflecting surface, and the land, and the pit, which is like a hole. So basically, scanning here with the laser, you have a different reflection, and the different reflection encodes different bit. So this is so it's very similar to our model. And so okay, so for instance, using quantum light, basically you could improve the readout in such a way that you could actually read something like this, or you can increase the capacity basically. So you can read memory which are unreadable by classical means, as well as you can increase the frequency of the light, so the capacity, and therefore the capacity of the optical memory. So you can imagine, you can have a compact disc at the UV range and even higher frequencies, but with organic layers. Another example is, for instance, the barcodes. So barcodes is based on reflection of light from bars and whites, so like this. So the same principle. And you can imagine a similar application here. So using quantum light, you could improve the readout in such a way that you can decode the barcodes which are unreadable otherwise, or you can even design very, very high capacity barcodes that you can only read using quantum light. Okay, that's all. Thanks.